Hello, my hardworking students. Today we're going to go through and cover the states of matter, which would make sense because the last thing we covered was matter itself and the different compositions it can have, whether we're talking elements or compounds or mixtures. So within that, looking at the different states can kind of impact that. As you remember, matter is anything that has mass and takes up space. In a simpler way of saying it, matter is basically stuff. If it has substance, it is matter. Energy is going to be the movement of stuff, and we'll talk about that when we get into physics, but right now matter is just anything that has substance, takes up space, and has mass. And we have four states of matter that we're going to get into. Solids, liquids, gases, and plasma. And the thing that distinguishes one from the next is the specific movement and behavior of the particles. And we're going to talk about the speed that the particles travel in and the energy that the particles actually have. And the difference in speeds, the difference in energy is what really dictates the state of matter that an object is in. Anyways, we'll go through in class and we'll actually talk about some of the animations here, and I have no idea why that one's in the top left. We'll ignore that. We'll hit these in class a little bit in the next couple days. But for now, a overview of what's going to happen here within the states of matter is that temperature really determines the kinetic energy. And when I say kinetic energy, I mean the energy of the particles. And if the temperature determines the energy of the particles, it's really determining the state of matter of a substance, whether it be a solid, whether it be a liquid, or whether it be a gas. And the particle movement itself is basically described by our kinetic theory's three parts, and we're going to call this the kinetic theory or the atomic theory. You'll see both of those used interchangeably throughout books and online and in class. So whether I say kinetic theory or whether I say atomic theory, we're basically talking about these three things. Basic idea is that all matter is composed of very small particles. Whether we're talking about a specific molecule, a specific atom, or a specific ion, we know that matter is composed of very, very, very tiny things. Those things are in constant random motion, as we see down here. If you go through and you kind of, I'll go back one slide and start over again so that you can actually see, the molecules are constantly moving around. And while they're in constant random motion, they're going to collide with each other and the size of the container. If they're within a container, they're going to collide with the size of it. If you're talking about the air inside the room, the particles that make up that air are constantly going to be colliding with either each other or the walls of the room or anything that happens to inhibit its motion. Okay? So all matter is made up of very tiny stuff. Those tiny things are in constant random motion, never quite know where they're going, and because they're moving around, they're going to collide with each other and sides of containers. And that's the basic idea of what's actually happening within every single kind of chemical reaction we talk about later in the semester, whether we're talking about solutions, whether we're talking about acids, bases, or whether we're just talking about the motion of molecules right now. It all comes back to what's happening within this kinetic theory. Okay? When we discuss solids, solids are very, very, very densely packed particles. Okay, there's very, very little space actually between the particles. It's almost like when you are at a rock concert. When I like to think of a solid, I like to think of the general admission floor at any kind of concert where everybody is so packed together that you really can't move on your own. You do what the group does. Okay? And they don't really move around very much. More than anything, they tend to vibrate against each other. And in the next couple of pages, we're actually going to see this picture start to move a little bit. This little GIF. But you can tell in this one, there's really no space between the particles. Okay? And a big key of all solids, they have a definite shape and a definite volume. Okay? Yes, I could go through and I could break a solid in half, but each solid has a specific shape and a specific volume that it takes up. Liquids, on the other hand, as we move our way from solids to liquids, there tends to be an increase in energy of the particles. Okay? As we increase the energy, the motion of the particles moves a little bit. You notice that this one has a little bit more space, and hopefully when we get to class tomorrow and go over the PowerPoints, you'll actually see the movement of it. But the particles have a little more space between them, and having a little more space, it's easier for them to flow around each other. So as we increase the energy, we also increase the movement of the particles. Okay? And that's really what's going on as we change from a solid to a liquid. And as that happens, we'd have no definite shape. Okay, a liquid, this same volume of liquid could fill any of these three containers, and I could take this same volume of liquid and put it into a squirt gun, and it could fill up that shape. Or I could put it into a crazy straw, and it could fill up that shape. Or I could dump it on the ground, and it would lay flat and take up that shape. But in either case, it has a definite volume, and the definite volume is very important there, because it's not gaining or losing an amount, but its shape can change. As we increase our energy a little more, we change from a liquid to a gas. And you kind of, obviously before it stopped here, you notice that there was a ton of space and a ton of movement going on between these particles. Basically, as we continue to increase the temperature, we increase the energy of the particles. And as we increase the energy of the particles, we go through and we increase the motion. Okay, the motion and the space between the particles. The big key is that the particles aren't getting bigger, there's just getting more space between them. Okay, and that's because they're so much energy that they're actually overcoming any kind of forces to pull them into each other. Right? So they have enough energy here to escape the attractive forces of other particles, and they are flying all around each other. Just like we talked about, solids tend to be like the main floor of a rock concert. I kind of like to think of gas as being like, hey, if you had a 6-year-old's birthday party after they just served cake and ice cream and took them to a park, they are going to be running wild all over the place. They're going to be running crazy, and you won't have any idea how to control them because they're 6. Okay. Gases also have no definite shape and no definite volume. The no definite shape should make sense. Whether we're talking about a single room, or whether we're talking about the gas being put into a bottle, or whether we're talking about into a car, or you breathe and it takes the shape of your lungs, you know that it can change shape. But the volume is something that we're going to go through and talk about a little more in depth when we get to the gas laws at the end of the chemistry unit. Okay. Within the gas laws, we are going to, a quick example of that is if you happen to go outside in the winter, and your car tires or your bike tires are not as inflated as they used to be, or you try to dribble a basketball or kick a soccer ball or pick up a football and the ball is not as inflated as it used to be, the volume of air can change based on temperature or based on pressure, and we'll look at that a little more later in the semester. When we go through and we think about plasma, plasma is one of those that you may not have been taught before. The big three were taught in elementary school, but plasma is basically just gas that has an electrical charge run through it. Okay? Plasma is created at very, very, very high temperatures, which is why it is most abundant and seen in stars, in suns, and in lightning. I'd say suns, our sun, but the stars and lightning. And because of this, it happens to be the most abundant state of matter in the universe, but it's not very abundant on Earth. So if you start discussing its abundance, make sure that you can distinguish between the universe and Earth. Okay? And obviously we can have changes in the state of matter. We know that, or we have seen that, temperature is going to influence the actual state that we're in. As you increase the temperature, you increase the energy of the particle, and as the particle has more energy, it's going to move faster and faster, and again, the space between the particles is going to spread out. I don't want you to think that the particle itself spreads out. As we happen to decrease the temperature, however, we're going to see an energy decrease in the particles, so they'll move slower, and the particles themselves will get closer together and be more compact. Okay? And we're going to look at examples of that in the next couple of pages. We'll kind of walk our way through how we change from solid to gas and back, or from solid to liquid and back, or how we go from gas to liquid and back. Okay? And really the only way that we get to plasma, and we're going to skip this one, is by taking a gas and running an electrical charge through it, or turning that electrical charge off, or electrical current, I guess. So we're going to kind of ignore this one for the most part, but we will go through in the next couple slides and hammer that triangle. Yeah. Solid to liquid and back. These are things that you should know, and it's the exact same temperature, but right now we've got the melting point. And the melting point is a point where solids become liquids, and the freezing point is a point where a liquid becomes a solid. Whichever way we call it, melting point means it's getting colder. Whoop, I lied. Melting point says it's getting warmer, and freezing point says it's getting colder. But these are going to be the exact same temperature. Okay? If we're talking about water, this temperature is going to be at 32 degrees Fahrenheit, or at 0 degrees Celsius. Okay? So it's the same temperature, it's just got two names depending on which way you're going. Are you increasing energy, or are you decreasing energy? Okay? Going from a gas to a liquid and back, we see the same kind of concept. We see the boiling point where a liquid becomes a gas. Sometimes you'll hear that called vaporization. An example is when you have water boiling on a stove. And this again happens when, if we're going from liquid to gas, your energy is increasing. Well, condensation is the complete opposite, where we're going from a gas to a liquid, like a mirror fogging up or doing grass, etc. And this is when your energy is decreasing. Okay, so it's the same thing in terms of temperature again, it's just you're going in different directions. And working our way back, we can actually go from a solid all the way to a gas and back, and those are kind of cool. Sublimation is when a solid goes straight to a gas. Our best example is dry ice. And then deposition is when you have gas going straight to a solid, when you end up losing a whole bunch of heat energy. And that's how hail and snow form sometimes. Okay, and again, same temperature, just your, in this case we are going through and gaining energy. In this case we're going through and we are losing energy. So that should have covered most of this triangle here, or given at least a quick example of all that stuff. For some of the, or a different way of looking at this stuff, we have phase change diagrams. Basically, on a phase change diagram, there is our axes are the heat energy going along your vertical or your horizontal axis, and we've got our temperature on our vertical axis. And as our temperature increases, you notice that we'll have solid, solid, solid down here, and at some point, and we talked about this, at the same temperature, depending on which way you're going, you'll have a melting occur if we're going from solid to liquid, or we'll have freezing occur if you're going from liquid to solid. And what I want to get across, or one of these points, is that you technically don't change from a solid to a liquid until this point right there. In this point here, you are melting, but you are still technically a solid. So this point right here, we're going to call this guy, I don't know, hashtag sign, is where you are finally fully a liquid. And then you'll be a liquid, and temperature will continue to increase. We'll change over to blue. And you go through vaporization. And at this point right here is when you are finally a gas. Okay, so we'll talk about this guy a little more in class, but that should hopefully make a little bit of sense. And every single substance is going to have a slightly different phase change diagram. Again, this kind of walks you through it, but at situation A, you are completely solid. At B, is both solid and liquid. At this point right here, you can go through and say you are finally C and you are entirely a liquid. At D, you are both liquid and a gas. And at this point right here, you are finally entirely a gas. Okay. A second thing that we can go through and see is obviously there will be slight differences for every single substance. And just like the phase change diagrams, we can look at phase diagrams, which is basically a way to represent different phases under different conditions like pressure or temperature. And every substance has a different phase diagram, but basically what this is saying if you happen to be at a certain temperature, a very, let's say, high temperature here, and a very low pressure, you're going to be in a gas. Or if you happen to be in a, let's say, a high temperature and a high pressure, this substance is going to be a liquid. Or if you happen to be at a very low temperature and a high pressure, it's going to end up being a solid. Or if you happen to be at a low temperature and a low pressure, depending on where it falls on this line, it may be a gas, it may be a solid, or this may be right at the point where you have sublimation occurring. Okay, so that's just a quick, easy way to see the entire spectrum of what could allow for solids, liquids, or gases for different objects. Anyways, that's about all the time we've got for this. We'll talk about phases a little more in class.